started here. So today we're going to be talking about structured support vector machines, and from there we'll move on to talking about convolutional neural nets. And I guess in some sense, I guess I think of CNNs as essentially now like just required background in order to have any sort of discussion about computer vision today. And so although many of you have actually seen CNNs before, many of you haven't, so it's still kind of a very necessary topic for us to cover. So the midterm exam is on Thursday at 6:30, so please be there a few minutes early just to find your seat. And these are now sort of our new plan for the dates of homework 3, which is to release it after the midterm. And I think we have yet to actually release on whatever the day that I say we will is, so we could probably add a couple days to that to get the actual date. Okay, so let's talk about structured SVMs. So the idea of a structured SVM is basically that we want to sort of extend the notion of a standard SVM in the same way that we sort of extended the notion of a perceptron to the structured case. And so here, what I actually want to start with is just a sort of an initial discussion of sort of a standard binary SVM, just so that we can kind of swap that back in, but also establish just some shared notation around this. So we can kind of think of this as our warm-up, thinking about SVMs. And I guess the first thing that we want to do here is just set up the standard quadratic program that one would solve for, or QP, to get back a support vector machine that maximizes the margin on the data set that you're given. Okay. So what this would look like is we're going to minimize over our weight vector W and our slack variables, we'll call them E. And the idea is we have two terms in the objective. One is the L2 norm of W, the quantity squared. And then the other is a sum over slack variables, where we have one slack variable per training example. And this constant C is just a hyperparameter that allows us to trade off between maximizing the margin on the one hand and minimizing the slack on the other. So we have some constraints here that we want to enforce. So namely, we want to say that each example is going to be correctly classified by some margin, but we're going to inject these slack variables so that if it's not correctly classified, you can still find a feasible solution here. So here, correctly classified just means that the predicted score is the same sign as the true label for the example. So, so here maybe it's good just to make an actual statement about the form of our data. So we could say that our data consists of n training examples that are these xi, yi pairs. And for each one, x is just our feature vector in m-dimensional space, and y is either +1 or -1. So with that statement in mind, now we can look down at the constraint that we're about to write and say, well, if yi is +1 and w transpose xi plus b is positive, then that whole quantity will be positive. If yi is -1 and our prediction w transpose xy plus b is negative, then that whole quantity will be negative. Or sorry, that whole quantity will again be positive. And the only time it'll be negative is if they differ in sign. So what we want to do here is constrain this so that this quantity is greater than or equal to 1 minus our slack variable, ei. And we're going to have one of these constraints for each of our training examples. And then the last detail is just that each of the ei variables is going to be greater than or equal to 0. That's also for all I. So this is the standard setup for an SVM. And we could say that the actual model that we're working with here is just going to be a linear model that predicts y hat, which is some h wb of x, as the argmax of y in +1 -1, or sorry, rather, just the sign of w transpose xi plus b. So, once we've set things up this way, now we can actually handle data that is not linearly separable. So if we have a bunch of plus points over here and a bunch of minus points over here, we'll be able to find a decision boundary between them with maximum margin. But we can also accommodate the case where we might have some plus points on the other side of the decision boundary, or some minus points over here. And in that case, the slack variables are going to essentially correct for the fact that yi times w transpose x plus b for those examples is actually going to be some negative number. And so when we get that, or it's going to be, say, less than 1, and for that case, we'll actually allow this ei variable to grow to some value greater than 0, and this allows us some flexibility to handle this non-linearly separable data. Okay, so the other thing to remember about SVM is that we can actually reformulate it in terms of a hinge loss. So a hinge loss is a loss function, L hinge, of a true y and a predicted y hat. And we define hinge loss to just be a max of 0 and 1 minus y times y hat. So this is a useful notion for us because now we can actually come up with a new optimization problem that is unconstrained. So the key observation here is that we can rearrange this this constraint that's trying to make sure that every training example is correctly classified, so that EI is sort of by itself. So that would look like EI is greater than or equal to 1 minus YI times W transpose XI plus B. And this is something that we could just sort of think of as at least having the same sign as Y hat. So what we have here is that we're trying to minimize this sum of these slack variables. And we know that all of the slack variables are going to be either greater than 0 or greater than this one. So we have that and EI greater than or equal to 0. So putting these two together, we get that EI must be greater than or equal to the max of those two. The max of 0 and 1 minus YI times W transpose XI plus B. So we can rewrite the problem as a minimization over just W, where now we have the term as before, that is minimizing the L2 norm of W. And as we know, minimizing this L2 norm of W is equivalent to maximizing margin. But now we have this additional term, which is C times a sum from I equals 1 to n. But this time, we actually take the hinge loss of each of these slack variables. So this is going to be the max of 0 and 1 minus YI times the prediction, W transpose XI plus B. Okay. So what we're trying to do is get back a model that has large margin and that has sort of few/small errors. So before we jump to the structured version of this, there's an interesting connection to be made once we've actually formulated the problem in this way. Okay. So let's look at two loss functions. Okay. So here, what we're looking at is the SVM problem. Oh, and actually, I guess we're yeah, this is fine. Okay. So what we're looking at are essentially the same sort of setup as before, except now you could think of this fi function, fi of yi, is equal to some feature function applied to xi and yi. So this just kind of keeps things a little more compact in this notation, so we don't have to write out all of the x's. So what we can look at is that on the top, we have the SVM problem, where what we're doing is saying that we want the difference of the score for, oh, you know what though? Maybe I should come back to this. We haven't talked about loss augmentation yet. Okay, so I'll make the observation now and then we'll come back to it again after we talk about loss augmenting. But basically what we're trying to do is say the score for the true thing, we want it to be much more than the max of the score for any other y. And what we're looking at in the bottom is what you get if you were trying to do, say, L2 regularized logistic regression, where again we have this W L2 norm term, that's the L2 regularizer. But then on the right, we're looking at the log likelihood of a log linear model. And so here, again, in the numerator for the log linear model, you have the score of the correct classification. And then you have the log of the denominator of, say, multinomial logistic regression, which is just summing over all of the possible output classes y, and for each one taking x of W transpose f of x and y. So these look really similar, except that one of them has a max over all possible y, and one of them has this log sum x over all possible y. So in both cases, we're trying to push the score of the correct thing up above either the next highest scoring thing or above everything that appears in the denominator. Okay, so how do we get to the structured version? Oh yeah.
There's an addition after you take the L2 norm, right? In slides there was a negative sign there.
Oh, yeah, so here they don't have a C, right? So they don't have any way of flipping the sign of this. So I guess maybe, I don't actually know what convention is. Maybe your reading actually uses plus. I used plus. So to me, the plus is more natural. Oh, I think maybe it's because of the max with 0. Yeah, so we should come back to this slide after we do the structured SVM version. And let's look at it again then. So what I wrote here, though, I definitely trust. Because what we did here was we said we're trying to minimize the L2 norm, and we're trying to also minimize the sum of these slack variables. You want those slack variables to be small. And as well, here, we also want to minimize this hinge loss. But I think what's happening in their version is they're saying, well, okay, we're gonna end up in a situation where we have this negative in front of the actual thing, the actual scores. And so I think they're just using that negative sign, but not including any hyperparameter to trade it. Okay. So, so the next thing that we want to do is look at just a slight variation of the SVM model that we already saw for structured perceptron. Okay. So the new model that we're going to consider here for structured SVM is we're going to assume a linear model. And here that would look like y hat. And we're also going to just go ahead and describe our data. So our data is going to be, as before, this collection of xi, yi pairs, but now xi comes from some set calligraphic x, and the vector yi comes from some set calligraphic y of xi. So the actual set of structures that's valid is constrained by the x. So, so if this was part of speech tagging, the sequence of tags that is your output has to be the same length as the sequence of words as your input. And so we're assuming a linear model here, which just means that as before, we would predict y hat as an argmax over, say, all possible y's for a given x. Oh, and let's go ahead and say that y hat is the output of some function h of x. So here we have argmax over all possible y's, where for each one we look at w transpose some feature function of x and y. So this is the same setup that we had last time, where we can now have features of the xy pair. So you could think about what we're doing as essentially building up to multi-class SVM, right? The same way that we were thinking about building up to multi-class perceptron. But here I'm kind of skipping that intermediate step, and let's just jump straight to thinking about this as there being exponentially many sort of possible outputs in the set yx as a function of the size of x. So here, what we'll do as well is this w transpose f of x and y, we're going to call this score s sub w of x and y. And this will just be the score of a particular xy pair. So what's interesting about writing it this way is, for now, we're just assuming linear models, right? So that it's really apparent, like, where the parameters are, what the features are, what's going on. But everything that we're going to do here is just going to lead up to the definition of a particular type of training objective. And if your scores were coming from somewhere else, like a deep neural network, or some sort of interesting kernel version of an SVM, then we could also make this work in that setting. Okay, but let's stick for now with the linear version. And so here, we're going to want to set up another quadratic program. And this time, the quadratic program is going to look pretty similar, but there's going to be some important changes. We have our model, our data. Yeah. Okay, so we're going to minimize, again, over w and our slack variables e. And the first term is the L2 norm of w squared. And the second term is our hyperparameter c times a sum from I equals 1 to the number of training examples n, and another sum, but this sum is a little more interesting. It's going to be over all of the possible y's that you could have for the ith training example. Right, so this is y in calligraphic y of xi. So inside that sum, we're just going to be adding up our slack variables, which are the ei, comma y values. Okay, so what's changed is now we have one slack variable for every training example and every possible y that you could get for that corresponding xi. Okay, so suddenly this is a lot of slack variables. We'll count them in a minute. And the constraints that we use for a structured SVM, the key idea is that we want to have the score of the true y actually be larger than the score of the predicted y hat. So this is sort of the basis of what we're going to be doing here. And so now we can come in and say that we want the score, SW, of xi, yi, to be, or the difference of that score with the score of every other possible y hat. Okay, so let's just pick one of them. So if we take the difference between the true thing and one of the possible things we could predict, we want that to be greater than or equal to 1 minus ei y hat. And so actually, just to be consistent here, in this first description, I'm actually going to go back and add a little hat to those y's. Okay. And then, as before, we want that the ei y hats are greater than or equal to 0. Now here's the key bit. That first constraint and the second constraint, we're going to want both of these to be for all I and for all y hat in the set y, calligraphic y of xi. Okay, so let's think about what it is that we're actually saying here. Maybe let's move this thing. So what we're saying here is that if we were to sort of line up all of the possible, so let's say that we have a word, or let's do part of speech tagging. So we have time flies facts. And this is our xi. And our yi is something like noun, verb, adverb. And so what the structured SVM is actually doing is it's saying, okay, well, let's look at the scores of all possible different taggings. Right? And what we want, okay, so here's yi, but here's another possible y hat, which would be, we could call it y hat subscript 1. And that could be VV network. And y hat 2 could be NN network. And y hat 3 could be VN network. So for each of these different possible labelings of the sentence, what we want is for the score S of xi and whichever of these we're thinking about, we want the score of the yi to be much larger than the other ones. Right? So ideally we have something like this has score 7, and then these ones have scores 5, 4, and 3.5. And so if we look then at the difference between this pair, the difference is +2 in favor of yi, and the difference in this pair is +3, and the difference in this pair is going to be +3.5. So the problem that we're trying to solve here is to choose parameters w such that we push the correct yi up above all of the other ones. And so we're essentially just enumerating every possible sequence of part of speech tags and constraining each one to be worse than the true thing. Okay, so here's where you should start feeling uncomfortable. Because, oh yeah, go ahead.
So our vocabulary here is just 3 tags, right? Just to make sure that there cannot be any B in there and no other combination.
Yeah, I mean, I guess really, maybe this list actually keeps going. So if this list were sorted by score, then hopefully we would have, like, let's imagine it is. So let's just say sorted by score. So in that case, yeah, we might actually have an additional y hat 4, all the way down to y hat last. But these are all going to have lower scores. Maybe the last one is like a score of -7. Y4 has a score of 0 or something like that. So there might be many other possible taggings, and we just need to make sure that the true one is scored higher.
So when we say that y hat is belongs to telegraphic y xi, that xi just puts a constraint on the length of the or anything else?
Oh yeah, in this example, it would just be on the length of the tag sequence. So there's lots of other things that we could have here, right? So if we were doing some sort of object detection task, then maybe we need to have the output variables represent bounding boxes in images, and so the bounding boxes need to be within the range of the actual pixels of the image. You couldn't have, so just do another example here. So for bounding boxes, this would be like, we'll be taking a look at these later. So if you have some image of a tree, and we're trying to come up with valid bounding boxes, this first one, call that B1, so B1, so X is the actual image, and then B1 is in Y of X. Okay, but here, if I made another bounding box, like this, call that B2, B2 is not in Y of X. It's just an invalid bounding box. So depending on the actual problem, we'll have a different definition of Y of X. Yeah.
So here the y hat is anything but the true label. I mean, y hat could have been the true label itself. In that case, how is that constrained?
Oh, whoops. Yeah, so we need to be more careful here, right? So this needs to be the set. So, well, I guess there's sort of two ways that we could do this. So one is we could just say that, just leave the set as is, and then you're just going to have some slack variable, which is for the actual training example itself. And that slack variable is always going to be equal to 1. Like, so there's going to be one slack variable that just has to be equal to 1 for every single training example. So I kind of prefer that way. The alternative is we could go back here and we could say, this is the set y of xi, and then just remove yi from it. Right? So it's everything except for that, which would also be totally valid. That's going to be yi when it appears. Okay, so this looks like a nice idea. So here now, I guess I have a question, which is how many constraints do we actually have in that actual QP that we just wrote down? I mean, we just wrote down a whole lot of constraints, and the question is, how many of them are there? Or equivalently, how many slack variables are there? So how could we write down a number that captures that?
N into the length of the
Say again?
N into the length of my
Yeah, so for our part of speech tagging example, it's going to be n times something. So let's actually give two answers here. So let's give a general answer first, right? So the general answer is, it's going to be n times, basically, however many things are in that summation over those y hats and y of xi, right? So we could write that as, this is just n times the max over all I of the size of y of xi. So basically, pick the largest size of that, and then we can just say that the total number of constraints is at least big O of this. We don't have to count them exactly. But if we wanted to do, say, an example here for POS tagging on only sentences of, say, length 23, which is the average length of, say, an English sentence in, say, Wall Street Journal text, then we would have something that is going to be the number of examples times, well here, we're going to have the total number of tags, right? Where there's often, and let's say 45 tags. So that would be n times 45 to the 23 power. So if we have 1,000 examples, it's 1,000 times 45 to the 23rd. Okay. So this is useless then, right? We can't possibly actually, give that quadratic program to a quadratic programming solver. So how do we fix this thing? All right, well, how about before we fix it, let's actually make it slightly more complicated. So I want to add an additional sort of key idea here is, so we said that we want the score of the true yi to be larger than the score of the predicted yi by some margin. And in this original version, we just used 1, which was going to get us that standard margin. But now I want the margin to be scaled by our loss. So what we can do is we can take the exact same quadratic program that we had before and replace this 1 with the loss of yi and y hat. So this is actually a fascinating change that we've just made here. Because what we're saying is now we actually want the margin to be larger for cases where the loss between the actual prediction and the true yi is high. So, for example, if we had, back to our example here, POS tagging, if we looked at, say, the loss of yi with the predicted value, then for the first example, the loss is just 0, right? Because it's exactly the same. And let's assume this is, assume something like a Hamming loss. So this is just looking at the number of tags that differ. Well now, so the first loss is going to be 0, but the loss of yi with y hat 1 is actually going to be a loss of 1 because it made one mistake on the first tag in that example. And then it made one mistake for y hat 2. And then it actually made 2 mistakes on y hat 3. So what we're getting at here is that however much the loss is, that's how much we're going to want the margin to be. So this is interesting because it actually solves the earlier problem that we had, which was we were actually including yi in the set of y hats, right? And so now we find that the slack change anything about the fact that we still have way too many constraints. Okay, so let's see if we can solve that problem. Okay. Okay. So this will be rely on the idea that we can sort of fold a maximization problem into our constraint. So what would this look like? Well, what we're going to do is we're going to say we want the score of xi and yi to be greater than or equal to the score of every other possible y hat. Okay? So let's just write that down directly as our constraint. So what would that look like? It would be a max over all y hats from the set yxi. And for each one of those, we want the score S of w of xi y hat to be less than or equal to the true score. Okay, so let's see. Can we stop here? Like, is this a good replacement for what we had up there? Or do we need something else?
Is it the same number of constraints?
So what we've just done here is we've said we're now, so we're now only going to have one of these constraints per example. So we still have, I mean, it's effectively taking those size of yi many constraints and packing them all down into one. Okay, but we left out some pieces here. So namely, we had a loss and a slack variable, so we don't want to lose those. So here we're going to say, okay, take the max of the score, but also that score, we should add to it the loss for that particular y hat. So this would be yi with y hat. Okay. So now, this is almost equivalent to what we had before, but here, this whole thing is basically the score plus the loss, right, of each of the other examples, and we want the score of the true thing to be higher than that for every single other possible prediction. And then we're going to be nice and add a slack variable by subtracting off just a single EI. So here, these n constraints and n slack variables replace the n times max size of y of xi constraints and slack variables from before. Oops. So this is our new constraint set. And just so that we're totally clear on what's going on, we could even just rewrite the whole thing, just so it's kind of all sitting in one place. So the whole thing would say, we're going to have max over W, taking 1/2 of the 2 norm of W squared. This time, we still have slack variables, but there's only n of them. And our constraint set is this. And also EI greater than or equal to 0. And this is going to be for all I only. Okay, so the question is, why on earth would we do this? Why would we fold this maximization problem into our constraints? Like, kind of like you said, right? Like, okay, technically we're down to n constraints, but it still feels like, effectively it's the same thing as before.
We don't have to solve the problem.
Yeah, so maybe what we could do now is play the same trick that we did with the standard SVM. Could we come up with an unconstrained version of this? So let's see what that would look like. So what if we took the standard QP, and now we did an unconstrained version, just like what we did with SVM, where here the unconstrained version is going to say, I wrote max, this should be min up here. This is minimizing, not maximizing. So now what we can do is we can say that we're going to take a min over all W of 1/2 of L2 norm of W squared plus C times I equals 1 up to n of another hinge loss, where the hinge loss looks almost like what we had before. But now think about what the constraints on EI are, right? EI is greater than or equal to 0, and it's also greater than or equal to the difference of this max term minus that score term. So we can do the same thing here, where now we just have a max over all y for yxi of S of W xi y hat plus the loss of yi with y hat. And then we subtract off the score S of W of xi and yi. So this thing, inside that summation, by analogy to the hinge loss that we were looking at before, is called a structured hinge loss. And so using this structured hinge loss is really important because it's going to allow us to solve this optimization problem with standard gradient methods. Okay, so here's where things turn fun. Okay, so if we want the gradient of this, then what we should observe is that, so let's call this structured hinge loss L sub SH for structured hinge loss. And you can see that the structured hinge loss is really just a function of our yi and our y hat, or sorry, our yi and our xi. So what we want to compute then is, and it's sort of a parameterized by w. So to compute the gradient, here we want the gradient of L structured hinge loss of, say, a single xi-yi pair. And what we'll find is that there's two terms that result. So does anybody remember how to take, does anybody know how to take subderivatives? This is probably something we haven't really talked about yet. Okay, so so let's look at, so let me write down what the gradient is, and then we'll look at why it's that. Okay. So whenever you have, or let's just do a quick example of the subgradient of max. So if we wanted to have a function that was max of 0 and x, and we plotted that function, then max of 0 and x is just going to be flat for values of x that are less than 0, and then it'll be linear for values of x greater than 0. So here, this is non-smooth, right? Because it has this kink in the actual function. But if you've worked with L1 regularization before, then you know that we can actually optimize in the presence of these sort of non-smooth functions. So this is non-smooth, but it is sub-differentiable. And what that means is that, you know, if we picked a point here and we wanted to know what its gradient was, well, it's just the slope of this little vector that's tangent to the line. And if I picked a point over here, its gradient is the slope of that vector. Okay. At the origin, there are actually many vectors that range between the vector immediately behind it and the vector immediately in front of it. And that set is called the set of subgradients. And so the key thing that we take away from this, though, is for stochastic subgradient descent, you can just pick one of the gradients in the subgradient and it will converge. So all we need is one of the gradients of this subdifferentiable function. Okay, so what are those? Well, it's either going to be 0, like the left side of that max of 0 and x plot, and that's for the case of if the structured hinge loss for this example is itself less than 0. Okay. And because we have to pick a value, we could even just say, or sorry, I guess it's never going to be less than 0. It'll either be 0, or if the inner part was, if the right-hand side was less than 0, then the whole thing will be 0. So we can just say, if the structured hinge loss is 0, then the gradient is 0. And otherwise, the gradient is just the gradient of the right-hand side, right? Which is just going to be the only two terms that actually involve W is the difference of those two scores. And so opening that up, we get that the gradient is just going to be the feature vector for xi, yi minus the feature vector for xi and y hat. Okay. Does anybody see any problem with what I just wrote down?
Why is the loss between the example and the label, like, shouldn't it be with the ground truth and the predictor? You use xi and y, but shouldn't it be y and y hat?
Yeah, so that's what we're getting. So remember here, let's go back up, that we said that the model is a linear model. So here we have the score itself, that SW of x and y, is just W transpose the feature vector f of x and y.
Yeah.
So going down, so if we take, so what we're doing is we're taking the gradient of just this inner part, right? And this is the difference of two scores, right?
Of like y and y hat, not x and y, right? I mean, like, I understand like y f is like x and y, but shouldn't the losses be in terms of y and y hat?
Oh, no, because we're doing something a little bit different here, right? So crucially, so this is sort of what I'm trying to get you to notice, is like, oh, well, let's make sure this is, oh, there's a minor typo in here that's super important. So this here is y hat, right? So under that max is a y hat. So the point is that y hat is bound by that max. Okay, but over here I didn't say what y hat was. Right? So this is where, like, this looks like a mistake. And indeed it is, because we haven't defined what y hat is. Okay, so we can define what y hat is. So this is why it feels like, yeah, this should be a loss of yi and y hat. But no, that's not what we're saying. We actually do mean it to be a function of xi and yi. And the key statement here is that we have where y hat is a particular y hat. And which y hat should it be? exactly. We have another max in here. So only one y hat actually participated in the computation of this loss. The other ones had score that were too low. So this is the y hat that is equal to the argmax over all y hats in y of xi, where now we have the one that had high score, s of xi y hat, plus hopefully low loss yi y hat. Excuse me. Okay, so we picked out the y hat that was basically the second best, or the one that was highest scoring among them all. Okay, so the last detail here is we can put this all together into an actual algorithm. So, I mean, we have an objective function, we have a gradient. Let's look at how you would actually implement this thing. Okay. So the algorithm is going to say, start by initializing your weight vector to say the vector of all zeros. Okay. And then following what we had done with perceptron, we're going to have an outer loop that says, while we have not converged. And then we're going to have an inner loop that says, for each xy pair in our data set D. Okay. For each one, we're going to solve that argmax problem that we just set up. So y hat becomes the argmax over all y hat in y of xi, where here we get the one that has highest score, s of w, xi, yi, plus loss. Oops, gotta be careful here. We don't actually have i's, right? I actually just rewrote it so that we're just getting these xi, xy pairs. So it actually kind of cleans things up a little bit for us. Okay. Okay, so now y is the ground truth, and y hat is our prediction. Okay. And what we then do is we say, okay, if the value of y hat that we're predicting here does not equal y, then we're going to update w to be the current value of w plus the feature vector of the ground truth minus the feature vector of the highest prediction that we made. And there's one more detail here, which is that at the end, regardless of whether or not we updated the parameters based on y hat, we're always going to update the parameters to be decreasing because of the actual W L2 loss term in our objective. And then at the end, we can return W. Okay, so some commentary here. So this score because we chose it to be a linear model, is just W transpose F of F of X and Y hat. So I had miswritten that as Y, but that's Y hat in there. So this is just the sort of highest scoring prediction. Okay. And then we say, if we're wrong, then increase the score of Y and decrease the score of Y hat. And then lastly, we have that there's this additional update. So as we're looking at this, you should start to notice that this whole thing is almost identical to the structured perceptron algorithm, but there's a few minor differences. So differences from structured perceptron. The first is this update because of the regularizer term. And the second is that we've included in our prediction this loss. And we actually call this problem loss augmented inference. Oops. Okay, so if we didn't have the loss there, and you had set up your feature function just as you did for structured perceptron, so that it was based on a factor graph, then you could solve that maximization problem with a mixed integer linear program, just as before. Okay. So the key remaining question is, can we efficiently solve this loss augmented inference problem? Right, where the loss augmented inference problem is just, predicting y hat as the argmax over all y hat of the score as a wx y hat plus loss of y and y hat, where this is the ground truth. Okay, so the answer is yes, you certainly can. And this is actually the problem that I had said that we would put in a homework, because it's such a good one to think about, which is essentially the same as an earlier question that we had asked, which was our minimum base risk decoder question. Where we had asked, if the loss function decomposes as according to some acyclic factor graph. Okay. So the sort of remaining piece of the puzzle here is just, how can we ensure that, you already know how to do map inference, okay? And basically we're kind of looking at a map inference problem here, but we've got this extra loss term. And the question is, can we basically fold that loss term into the map inference problem such that the whole problem just looks like another map inference problem and we can solve it as we usually would, with belief propagation or with a mixed integer linear program. So on your homework, we'll actually ask you to kind of show that if the loss decomposes correctly, then you can reformulate it as just another factor graph with a map inference problem to be solved. So we'll stop there. And let's take questions outside. Oh, sorry, lambda is, great question, let's not stop there. Lambda is the, sorry, this is by analogy to, so like the weight on the regularizer. I should have done this in terms of, this is a function of C. So I should have written it as like, I think it would be like 1 over C. Yeah. If y hat not equal to y?
Like you only want to consider weight if y hat doesn't equal y.
Yeah, that's right. So if we make a mistake, it's kind of like a perceptron update. Oh, okay, thank you. All right, now we're truly fixing all the errors. All right, great, thanks guys. You can stop me in the middle when I'm making these sorts of errors too. Great.